Welcome back. This is the final lecture in the series of lectures on gamma decay. We'll address few related topics. A detailed presentation of gamma decay or the rate at which gamma rays come out is not possible because to do it from first principles, you need quantum theory of radiation, which is beyond the scope of this course. But we'll give some general ideas that uh, are utilized here. It is seen that the transition probability of getting a gamma ray out depends upon the radius of the nucleus divided by the de Broglie wavelength to the power of 2L. Okay, so this L quantum number we had introduced in the last few lectures. We know the formula for de Broglie wavelength. So if you implement this, you get some such value. And when you take this value, and typically you know this is a formula which we had introduced in some previous lecture, where R is related to atomic weight of the nucleus. When you substitute that, you get this quantity. This quantity is found to be less than 1, typically, because the transition probability is given by this quantity. When R by lambda is less than 1, this suppresses this nature, mathematical nature of transition probability, suppresses the generation of multipole radiation with higher lambda L. Okay, so if this is a quantity less than 1, so as you increase the power, the transition probability will become lesser and lesser. So that is one mathematical justification why you don't see higher multiples, even though it is theoretically allowed. So again, none of these formula will be derived, but we just present the formula. So this refers to decay constant. Okay, so we have run out of Greek symbols. We are using Greek symbol for wavelength, lambda, and also for decay constant. So the decay constant for electric gamma transition is given by this formula. For magnetic multipole gamma transition, gamma decay is given by this formula, wherein S is a complicated quantity related to L. We are not deriving any of this, neither does this book derive, but there are some references in this book which gives you and where you can find the derivation. In any case, within the scope of this course, these derivations are not required. So with all these things, you can, for different L's, you can get S. What is important? Okay, so what we want to get an idea is, so there's a typo in the book, so you have to be aware. So this refers to the decay constant via electrical multipole transition divided by the decay due to magnetic multipole transition. That's what we want to get to, which is more possible. Okay, so when you divide this by this, you get this formula. We have already seen a formula for radius of the nucleus, how it is related to the atomic weight of the nucleus. When you put this in together, what you see is that the electrical multipole transition becomes more and more possible with increasing atomic weight. Okay, so that's what you see. Okay, so we had introduced in the series of lectures why a change in, we have classified the multiple radiations into two categories. Change in charge distribution will give rise to electrical multiple radiation. Change in current distribution will give rise to magnetic multiple radiation. So what you see is that this electrical multipole radiation becomes increasingly possible as A increases. All right. At least this is the functional relationship. Okay. It goes as this power. So there are a few other minor topics to wrap up. So this gives you decay constant for gamma radiation. So we said there are other mechanisms for gamma transition, and one is internal conversion, right? So because of the electromagnetic interaction between the nucleus and the electrons that exist outside the nucleus, electron from some shell will be emitted. So the energy involved is given by this. ED refers to the difference in the energy of the nucleus when it goes from the initial state to final state. ED is that energy difference. And this is the energy required to remove the electron from its shell. So the overall energy involved is this quantity. So what is of interest is which is more possible, okay, the rate of internal conversion or rate of gamma emission. All these things are competing processes. So of course, rate of internal conversion depends upon the shell from which electron is removed. This typically in principle can vary, while it in principle can vary from 0 to infinity. Typically it is seen that rate of gamma emission is much more than rate of internal conversion. Okay. So whenever you have an internal conversion, there is a vacancy of an electron from a shell. So typically, all these, when you see a vacant electron, there is a process called Auger process. Okay, so that it's a French name, so these French pronunciation are rather not obvious. Supposedly, this is pronounced as Auger. It's named after the person who observed this. So he found that, so there is, we won't go into this, but typically, Auger electron means there is a vacancy of an electron from one of the shell. And whenever there is one such and that vacancy is typically generated when the atom is exposed to X-rays. Okay, so that was the way it was first documented experimentally. Whenever you have one such vacancy, an electron from the outer shell will fill in this vacancy, fill in that hole, which would give rise to an energy transfer, right? This energy transfer might in turn give rise to some other electron emission. Okay. So why we are dealing with this is because this internal conversion gives rise to electron vacancy. How that electron vacancy is filled is via these kinds of processes. And electron from an outer shell jumps into the hole that was there, and which also gives rise to further energy release. With this, we are concluding our discussion on gamma decay. So we will switch gears and take up a new topic via a series of lectures. We will start our discussion on nuclear reaction from the next lecture. Thank you.